Good day, everyone. Welcome to the first ever vlog for structural theory. Now, we are going to discuss the determination of deflection for a beam using double integration method. So, as you can see here, we are given a beam. This is a simply supported beam with roller support here and hinge support here. So the beam is loaded with a 4 kilonewton per meter load, which is uniformly distributed over this entire span of 4 meters. So the span is 4 meters. And then we have also another load which is given. You have 8 kilonewton, which is a concentrated load applied at 1 meters from the hinge support. Then we have another 4 kilonewton per meter, which is also uniformly distributed, but this time the distribution starts at 2 meters from the roller support. So we are also given here the cross section. This is the section, the cross section of the beam. The beam is 200 mm in width. The depth is 450 mm. So the depth is 450 mm while the width is 200 mm. So the question is, we are going to determine the deflection, take note, at the mid span. So meaning we are going to determine the deflection at this point of the mid span. So what we are going to do using double integration method is that we can cut a section here. In cutting this section, we can say that the distance here, we can say that this is x. So the first thing that we have to do is to determine the reactions at the supports. So let's say we use the reaction here as V, and then we use letter R to denote the reaction at this portion. So next, we are going to continue our computation by determining the deflection at the mid-span. So the first thing that we have to do is to determine the reaction at the beam. So this is our beam, and we are going to determine the value of the reactions at the hinge and the reaction at the roller support. By the way, for hinge, of course, we have vertical and horizontal reaction. For roller, we only have vertical reaction. But since we are dealing only with gravity load here or gravity forces, so we are just going to make use of the vertical component for the reaction at V or at the hinge support. So the first thing that we have to do is to determine the reaction by taking moment at either supports. So if we are going to take moments at either support, if it takes, let's say we take summation moment at R is equals to 0, then we can have equation of 4 times B, which is equals to 8 kilonewton. Perpendicular distance is 1 meter, 3 meters from R. So you multiply it by 3. Plus, we do have the 4 kilonewton per meter uniformly distributed over the entire span of 4 meters. So we are going to multiply it by 4 meters. And then the perpendicular distance of that equivalent concentrated load from R is half of 4 meters. So that is why you have 2 meters. And then we have another load which is uniformly distributed 4 kilonewton per meter. But this time it's only 2 meters from the roller support. So that means we are going to multiply it by 2 meters. And then the perpendicular distance of that equivalent concentrated load. By the way, the equivalent concentrated load is located here, is half of the 2 meters. So that is to be multiplied by 1 meters. So that means if we are going to determine the value of B, by the way, this 4 here stands for the 4 meters here. So you multiply 4 by the value of the reaction, it should, if you are going to take moment at the roller supports. So this would give us a value of 16 kilonewton. And now we shall take summation moment at V is equals to 0. And taking summation moment at V is equals to 0, we will have 4 times R is equals to. Again, we have 8 kilonewton here, but this time the perpendicular distance from hinge support is only 1 meter. So you're going to multiply it by 1 meter. Plus, of course, again, you have the 4 kilonewton per meter, which is uniformly distributed over the entire span of 4 meters. So we are going to multiply it again by 4. And then, of course, you have the perpendicular distance from the equivalent concentrated load. That is half of the 4 meters. So you multiply it by 2. Plus, we have this 4 kilonewton per meter. You multiply it again by 2 meters. And then this time, the equivalent concentrated load is at 3 meters from the hinge support. So we are going to multiply it by 3. So therefore, you would have the value for R, which is also 16 kilonewton. So we have here 16 kilonewton for the value of B and another value 16 kilonewton for the value of R. Those are our reactions. Now going back to our figure here, we are going to write down the moment equation by taking, again, a cross section here. So cutting a section, I mean. And let's say that this is at a certain value of x distance from the hinge. Remember that from our computation, the value of B is 16 kilonewton. Okay, so this is 16 kilonewton. So you can take moment in this left portion of the cut section in order for us to have the moment equation. The moment equation is equivalent or should be equated to EIY double prime. Going back into the moment equation, we are going to equate EIY double prime is equals to the moment at the left. And you would notice that what we did was to cut a section here. We cut a section and that is at a distance, certain distance, x from the hinge support. So what we are going to do is to take EIY double prime is equals to the moment at the left. Wherein M sub L here is our summation of moment at the left portion. So This moment equation shall be the one that we are will be the one that we are going to use to determine the value of the deflection. Remember that E is the modulus of elasticity, I is the moment of inertia, and Y is the deflection. So since we are using here double integration method, we are going to use the moment equation as our reference in the integration. So we are going to integrate EIY double prime or the moment equation to give us the value of EIY prime, which is our slope equation. So if EIY double prime is moment equation, EIY prime will be the slope equation. And then further integrating EIY prime, we will have EIY, which is equals to our deflection equation. So we have three equations here, and the last equation will be used to determine the deflection, which is denoted by the variable y. So let us write first the moment equation. The moment equation, we take moment at the left portion of the cut section. Remember that this is 16 kilonewton and that the distance from the cut section up to this point is x meters. So we have 16 kilonewton going in the clockwise direction. You multiply it by the distance, which is x. And then we also have 8 kilonewton, which is going now in the counterclockwise direction. So by the way, our sign convention is clockwise for clockwise positive, counterclockwise negative. So since the 8 kilonewton is going counterclockwise, we're going to use minus sign. And then you would notice that the distance of 8 kilonewton from here, if this is x and this is 1, then this distance will be x minus 1. So we are going to write it in the pointed bracket, x minus 1, which is the perpendicular distance of 8 kilonewton from the cut section. And then we have 4 kilonewton per meter. So this 4 kilonewton per meter is going also in the counterclockwise direction. So negative 4. And that the distance here is x. Take note, this is x. That is x. That is the equivalent concentrated load. But if you still have to multiply it by the perpendicular distance of equivalent concentrated load from this point, that would be x over 2. Then we have another 4 kilonewton per meter, which is going in the counterclockwise direction also. So that is 4. If this is x and this is 2 meters, so that means this is x minus 2. So we write it inside the pointed bracket, x minus 2. And then, of course, you would have half of the distance x minus 2. So x minus 2 divided by 2. The value of x minus 2 over 2 is the perpendicular distance of the equivalent concentrated load of 4 kilonewton per meter times x minus 2. So this will be our moment equation. Let us first simplify the moment equation. And this would give us 16x minus 8, x minus 1, 4 divided by 2, that would be negative 2x squared. And this would become negative 2 quantity x minus 2 squared. So there you go for our equation of moment. We are going to equate it to EI y double prime. Again, E is the modulus of elasticity, I is the moment of inertia, and Y is the deflection. So we are going to equate it with 16x minus 8 times x minus 1 minus 2x squared minus 2 times the quantity x minus 2 squared. So this will be our equation, moment equation. The value of the modulus of elasticity is dependent on the kind of material that you're going to use for the beam, while the value of the moment of inertia is dependent on the cross-sectional shape of your beam. So we are going to integrate this equation. So if you are going to integrate EIY double prime, we're going to integrate the entire equation. This would give us EIY prime. The integral of 16x, if you are going to integrate, let's say for example, you are going to integrate x squared. The integral of x squared will be equal to x cubed over 3. Or that is simply stated, if you are going to integrate x raised to the n power, that will be x raised to n plus 1 over n plus 1. So we will have here 16x squared over 2 minus the integral of 8 times x minus 1. So the integral of 8 times x minus 1 will be 8 times x minus 1 squared over 2 minus the integral of 2x squared. That will be equal to 2x cubed over 3 minus the integral of 2 times x minus 2 squared. So that is 2 times the quantity x minus 2 raised to the third power over 3. And don't forget to add c sub 1. That is our slope equation. If we are going to simplify the slope equation, EIY prime is equals to 8x squared minus 4 times x minus 1 squared minus 2/3 x cubed minus 2/3 times x minus 2 raised to the third power plus c sub 1. So this is our slope equation. This is our slope equation. Remember, we are writing the deflection equation that we are going to use to determine the actual deflection of the given beam. So we are going to integrate. This will be the second integration. That's why we call it double integration method. We have E, I, Y. This will be equivalent to 8x cubed over 3 minus 4 times x minus 1 cubed over 3 minus 2 third x to the fourth power all over 4 minus 2 over 3 times the quantity x minus 2 raised to the fourth power all over 4 plus c sub 1 x plus c sub 2. So this will be our deflection equation. EIY is equals to 8 over 3 x cubed minus 4 third x minus 1 cubed minus 1 sixth or x to the fourth over 6. This would cancel out. This would cancel out. This would become 2. So you have x minus 2 raised to the fourth power all over 6 plus c sub 1 x plus c sub 2. So again, this is your moment equation. We wrote the moment equation to be used in the double integration that is equated to EIY double prime. Now we integrate EIY double prime, it would yield to EIY prime. And integrating again EIY prime, we will have EIY, wherein EIY is what you call as your deflection equation. So we will have EIY is the deflection equation. So this is moment equation, slope equation, and then you would have your deflection equation, which we are going to use to determine the actual deflection of the beam.